In this session, let us try to understand some basics. After these basics only, we will be able to enter into the original machine. Already, we had a discussion about small introduction at least, about transformer, kind of why we use magnetic material, at least for time being, in order to reduce leakage, we can say, for time being. And why we use many number of turns in primary, such that even though current is less, operating flux can be more, because magnitude of operating flux not only depends upon magnitude of current, but also on number of turns. Now if you think of in secondary, why we increase number of turns? In order to increase output voltage for time being. Now we have to understand Phasor concepts. Means that one thing, by end of this discussion or session, you should understand that, or you should fall in love with sinusoid. Okay, because in machines and power systems, we love sinusoid to such an extent that if any non-sinusoid is there, that non-sinusoid we will convert into different forms of sinusoids by using Fourier series, and except the basic sinusoid or fundamental, remaining all we will call them as a harmonics. Okay, so let me repeat again, why we love sinusoid. Okay, or means we will see only in AC machines, we will see only sinusoid, and apart from sinusoid, if any other non-sinusoid come, that non-sinusoid we will convert into different frequency sinusoid components, and we are going to take only fundamental, and remaining all we call them as a harmonics. Okay, by Fourier series. Anyway, point here is again why we love sinusoid. Okay, so means we can say that means some students have these answers, like this is ISC Bangalore interview question. Okay, so anyway, point here is, maybe some students say that generation of sinusoids is easy, that's why we use sinusoids. Is generation of sinusoids is easy? Yes. Generation of sinusoids with different frequency components will be easy, provided those sinusoids are signals. Okay, for example, because that is right in control systems. Okay, but that cannot be right. Maybe that can be right even in analog electronics also, because they deal with signals. Okay, but we deal with bulk of power, huge of power. Okay, so the moment huge bulk of power means our power handling capacity is in MVAs. Okay, so if you think of MVA, generation of sinusoid is not easy. We have to struggle a lot in synchronous machines. We go ahead with distribution of winding, we go ahead with short pitched winding, and we do many things in order to reduce components of harmonics, and in order to make my induced voltage as more sinusoid as possible. So generation of sinusoid as a signal is easy, but generation of a sinusoid for bulk of power for our electrical engineers is not that much easy. Okay, so generation of sinusoids is easy with different frequency components is right from control systems point of view, but in machines we should not say that. Maybe some guys say that, sir, if I take sinusoid, okay, if I integrate or differentiate sinusoid, output is going to be sinusoid only with some phase displacement. Okay, is it right? Yes, that is right. Again, that is not from machine's point of view, that is from communications point of view, because signal propagation will be easy, like if you have mathematically if you have sinusoid, because differentiation of sinusoid is a sinusoid and integration of sinusoid is a sinusoid, so that is advantage, that is true, but from communications point of view, not from machine's point of view. Okay, some say that means like we have different frequency domain tools, like maybe in control systems Bodo plot is there, Nyquist plot is there. Okay, so we have some frequency domain tools such that even if you give any non-sinusoid to the system, that non-sinusoid can be converted into so many components of sinusoids. For example, if I have the system, for this system, maybe this is the input, this is the output. Okay, so this is the system. Now for this system, if you want to expect the magnitude of output for a non-sinusoid input, for example, a triangular input I would like to give as an input, then what I can do, I will give this particular triangular input to the Fourier will divide it into fundamental component and maybe third harmonic component, okay, and maybe fifth harmonic component, or maybe kind of. Why I am saying harmonics is because in machines other than fundamental we call them as harmonics. Okay, anyway, what I do is fundamental, I will give it as input, I will calculate output. Okay, and maybe other frequency component, I will give it as input, I will find output, and maybe other frequency component, I will give it as output, input, I'll find output. Now means addition of all these components of sinusoids will be the triangle, and addition of all these sinusoid output components is going to be the exact output for the triangular input. That is true. That is true. So the moment like if you want to use Fourier series, means we can say that we have S frequency domain tools like Bodo plot, Nyquist plot, many frequency domain tools are there. So frequency domain in the sense sinusoids. Okay, so the moment you have many frequency domain tools, we are going to use sinusoid is again wrong, because that is meant for again control systems. Okay, basically for any non-sinusoid input, that can be split into so many sinusoid components, and those sinusoid components each and every one individually if you apply, okay, the output is going to be again sinusoid, provided the system is linear, of course. Okay, so again is going to be output. Addition of all these sinusoid inputs combinedly can give you non-sinusoid input. Addition of all these sinusoid outputs can be combinedly, we can get as a solution to the problem. But again, means anytime have we used Bodo plot in our machine, our power system, Nyquist plot. Okay, so point here is, means that can be right from control system point of view at the signal level, in the feedback path. Okay, but if you think of our machines, so not because of that, not because we have Bodo plot or Nyquist plot or some frequency domain tools, we are using sinusoid in our machines or power systems is wrong. Okay, so means these are right depending upon the subject we are going to handle, but in our machines and power systems we love sinusoid not because of all these three things. Okay, it's not because we have frequency domain tools, it's not because generation of sinusoid is easy. Okay, so point here is why we love sinusoid then in machines and power systems. Basically we love sinusoid because the rotating magnetic field, this particular concept will come in induction motor. Okay, so basically means out of complete power generation in any country, maximum portion of power generation will be consumed in the name of induction motor. Okay, so in any country, because most of the drives are induction motors. Your ceiling fans in induction motor, means if any farmer uses maybe water pump, okay, so that will be induction motor. Okay, most of our utilities based on induction motor. Okay, so the moment you want to have means mechanical power output, means normally we use induction motor because induction motor is most rugged machine. Okay, most rugged machine means the best rugged rotating machine is induction motor. Okay, so means basically in any power generation in any country, maximum percentage of power generation will be consumed in the name of induction motor only. So in generation we have to keep in mind induction motor. Okay, now induction motor work on the principle of rotating magnetic field. Those concepts we will see in induction motor, and in order to have better rotating magnetic field, our input voltage to the induction motor should be sinusoid is right answer for machines. Okay, so from machines point of view, why we love sinusoid? It is because of induction motor. Because maximum percentage of power generation will be consumed in the name of induction motor. Induction motor work on the principle of rotating magnetic field RMF. Okay, and better rotating magnetic field can be produced if you use sinusoid. That's why we love sinusoid in machines. AC machines at least, because DC machines frankly we don't have any application. So from now onwards means we struggle hard for sinusoids. Okay, now with sinusoids there is a problem. What is that problem? Kind of, for example, if you have a small system maybe with 5 nodes, okay, so maybe 5 nodes are there. Okay, or maybe 10 branches are there. In this 1, 2, 3, 4, 5 nodes, and maybe branches connected. Okay, so these are the branches connected such that 10 branches are there. Okay, now what is meant by analysis from network theory, mesh analysis, nodal analysis, or in our power systems load flow studies? Okay, so what is meant by load flow studies? For example, each and every node voltages we should be able to find. Each and every node voltages we should be able to find. Each and every branch currents we should be able to find. We should be able to find each and every branch currents. Such that of course under healthy or contemplated conditions we will see in power systems. Okay, so in mesh analysis also what you do, we will try to find out currents. That currents multiplied by those impedances will give you the voltages. Okay, now what do you do in nodal analysis? Directly you will find voltages. Okay, and by finding voltages you can find current flowing through any branch. So what is meant by analysis? Voltages at each and every node should be found. Currents flowing through each and every node should be found, such that maybe we will be able to find power generated or power absorbed or active power or reactive power or apparent power or power factor. Anything can be found. Okay, so maybe for example, for this, if I would like to draw the output voltages and currents, okay, maybe my node 1 voltage is this. Okay, for example, node 1 voltage is this. Now let us think of node 2. Okay, so this is node 2 voltage, and node 3 voltage maybe this, maybe from here node 3 voltage is this. Okay, similarly, how many waveforms we are supposed to draw? Okay, 5 node voltages are there, 5 nodes are there, 5 node voltages and 10 branch currents, total more than 10 voltages and currents we should be able to draw. Now, why we use phasors? Basically, we are engineers, or means we are lazy fellows, frankly. Okay, so if something is required, we go to any extent to find it. But if something is not required, we don't do it. Now, even when something is required also, we will try to search for the easiest way. For example, if I want to represent in one, what is the time period, 10 waveforms, sinusoid waveforms, is it possible for us to draw 10 waveforms? No, it's not possible. So, means we are looking for some other domain. In that particular domain should be able to remember whatever the information is required to be remembered in drawing this. In the sense, I don't want to draw the waveforms at all. Okay, I don't want to draw the instantaneous values. I don't want to draw the waveforms of different voltages or currents. Okay, but I want to remember the information. That is phasor. Means that, for example, if you think of this red sinusoid waveform, maybe amplitude should be remembered. Okay, what are the information we are supposed to remember such that we need not draw these waveforms at all? Okay, because sinusoid, that's already fixed. Okay, so the moment sinusoid, everything is going to be sinusoid only. So we are thinking how to remember sinusoidal information without actually drawing the waveforms. And time period should be remembered. Our time period is nothing but frequency terms also, I can say. Okay, so amplitude should be remembered, frequency should be remembered, and with respect to one reference phasor or with respect to one reference sinusoid, means at how much is the displacement angle, pi, if I think of, means pi is the displacement angle between this voltage black and voltage red. This also should be remembered. Okay, so my new domain, that is nothing but phasor. In my new domain, if I can remember these three things, in future, if I want to really draw the waveforms, I'll be able to draw. Okay, so we are looking for a system, okay, in which I can avoid drawing the sinusoidal waveforms. That is nothing but phasors. Now let us see how this particular phasor concepts is able to remember that. Now, for example, this is the voltage. Okay, so this is sinusoid and this is omega t or 2 pi of t. Okay, now what are the things that has to be remembered if I consider this voltage as a reference? Okay, so the first thing is amplitude should be remembered. Amplitude should be remembered. Second thing is frequency should be remembered. Yes, this is the reference phasor. Yes, this is the reference phasor. Directly I can think of drawing the phasor. For example, with this amplitude, if I can draw a line. Okay, so what is that line amplitude? For example, if I think of this is V1. Okay, V1, what is the amplitude? V1 maximum. Normally I show with upper arrow. This is my tradition, I use that way. Okay, so if this length is V1 maximum, now length is remembered or not? Yes, in the sense amplitude of the signal is remembered. Now what has to be remembered? Second thing is speed. Okay, omega. So for example, if I assume that if it is rotating in anti-clockwise direction with omega speed, now second thing is remembered. Now if it is rotating in that way, for example means this is going to be my phasor is rotating in this direction with omega. Now let us see horizontal. I'm going to show you some GIF files also. Let us see that horizontal reflection of this particular line on a plane. Okay, so as of now, for example, this is V1 maximum. Okay, as of now, if I see horizontal reflection, how much is the reflection here? For example, this is the reflection. Now if I see horizontal reflection, how much is the magnitude of the reflection? 0. Okay, 0. Now for example, if it reach this point, because it is rotating in anti-clockwise. Why anti-clockwise? I'll tell you. Means it is rotating in anti-clockwise direction. Once it reach 90 degrees, how much is the horizontal reflection? Is going to be maximum. After 180 degrees, horizontal reflection is going to be 0. After again 90 degrees more, horizontal reflection is going to be negative maximum. Again after 90 degrees, it is going to be 0. For example, if I take at any angle here, because my phasor is assumed to be rotated in anti-clockwise direction with omega. Okay, so for example, this is theta. Okay, now what is this particular length here, height here is nothing but hypotenuse, okay, into sine theta. So I can say that this is going to be maximum value because the amplitude is considered as length of the phasor. Okay, so under that conditions, for example, when the phasor is rotating, if you stop the phasor at this point, what is the horizontal reflection here? Horizontal reflection here is nothing but the height. What is that height? Peak value into sine theta, opposite side. So I can say that horizontal reflection will give you sinusoid. Okay, so rather than drawing this sinusoid, if I draw with a single line, it is sufficient that single line length of this line should be peak value. And it should be rotating in anti-clockwise direction with omega. Then if you think of horizontal reflection will give you the same sinusoid. So we need not draw sinusoid at all. Or whatever the information my sinusoid is giving, the same information here also will give you amplitude, it will give you frequency, it will give you, because it is the reference phasor. About pi I will tell you. Okay, now let us see this. Okay, so this is going to be length of the phasor. This is going to be length of the phasor. Length of the phasor is nothing but peak value. Now if you see horizontal reflection, which will give you sinusoid or not? Yes. Now I am assuming that it is rotating in anti-clockwise direction with omega speed, such that my horizontal reflection will give you the sinusoid, okay. Now let us come back to, of course, vertical reflection is also possible, okay. So vertical reflection is also possible. Let me think of vertical reflection. If I see vertical reflection, it is like this, okay. So horizontal reflection will give you sinusoid, vertical reflection also will give you sinusoid, of course with 90 degrees phase displacement, okay. Now anyway, let us come back to our previous discussion, okay. Now we came to know that rather than, what do you say, drawing the sinusoidal waveform, you can remember whatever may be the information it is giving by drawing a one small line. That line length should be equal to the amplitude value. For example, if I have maybe voltage here, voltage waveform is this is reference. Now let us think of my current waveform is like this. My current waveform is this, okay. So means how to represent these two waveforms, because voltage, black line is going to be the reference, and with respect to black line, red line, let us see, okay. Means that how to draw this, very simple. Length of the phasor should be peak value, okay, and it is starting from 0 only. So for example, this is V1 maximum, which should rotate in this direction, omega, okay. Now what is the length of the phasor of the current, red line, length of the phasor of the current is this, okay. And whenever voltage is 0, for example, at the instant of voltage 0, my current is having negative value, okay. So whenever the voltage instant value is 0, my current instant value is negative, and it is running towards 0. So if I want to draw current waveform, I1 maximum, okay. So this is going to be I1, and this is V1, okay. Now if you see, if both are rotating in anti-clockwise direction, as of now, if I see horizontal reflection will give you 0. For example, let me draw, okay, horizontal reflection of this. As of now, horizontal reflection will give you 0. It will start from 0, okay. As of now, whenever my voltage instant value, horizontal value is 0, my current instantaneous value is negative, and it is running towards 0, and length is less, so peak value is less. So rather than drawing these two waveforms, if you can draw two lines, it is sufficient, okay. Now means voltage is there, current is there, which is lagging, which is leading. We should focus here, because in drawing the basically transformer, we have to understand the phasor diagrams properly, and in synchronous we should be able to play with the phasor diagrams, and in induction without phasor diagrams also problems can be solved, and in DC there is no concept of AC at all, so phasor diagrams will not be there, okay. Now first of all, let us try to understand which is lagging, which is leading. For example, if you see here, my voltage 0, positive 0 I say, because it is 0 and it is about to go to positive, so I call it as positive 0. So voltage positive 0 is happening at omega t equal to 0, okay, because basically this is omega t, okay. So voltage positive 0 is happening at t equal to 0, omega t equal to 0, and current positive 0 is happening after some time. So we say that with respect to voltage, my current I1 lags V1 by, for example, this is pi, angle pi, okay. So by pi we say, okay. Now my current is lagging behind voltage by 90 degrees, or with respect to my current. For example, my current positive 0 is starting at here, and my voltage positive 0 already started. So with respect to my current, my voltage is leading ahead, we can say, by pi degrees, okay. So for example, here voltage, whenever voltage is 0, current is negative and it is running towards 0, positive 0. Now, point here is one thing, okay? For example, if you sit here on voltage, of course, I'll repeat multiple times in phasor diagrams of transformer, okay? So, if I sit on voltage, both are rotating in this direction with the same speed of omega. Okay, so voltage and current both are rotating, the phasors are rotating is the assumption, right? So if both are rotating in anti-clockwise direction, if I sit on voltage, in order to look for the current, I have to look back. What do you say? Okay, so if I sit on voltage here, in order to see the current, in order to look for the current, means everything is rotating in anti-clockwise direction. Remember, everything is rotating in anti-clockwise direction. So if you sit on voltage, you have to look back for current. So I can say that current I1 lags V1 by pi degrees. Okay, or for example, if you sit on current, both are rotating in anti-clockwise direction. If you sit on current, you have to look forward for the voltage. So with respect to current, my voltage is leading ahead by pi degrees. Now here, whatever may be the phase displacement between voltage and current, which is pi, okay, is constant. Whatever may be the pi here between voltage and current is going to be stationary, we say. Why? Because see, this pi is constant or not? Yes. Now voltage is rotating with omega and current is also rotating with omega. So this pi is going to be stationary or not? Yes. Okay. So for example, as of now at omega t equal to 0, voltage is 0. Okay, and after pi, current is coming to 0. Now if you see here, as of now voltage instant value is 0, and after pi degrees, in the sense after pi I1 should come here, voltage should go here. Okay, after pi I1 will come here, after pi I1 will become 0. So this angle is going to be pi only again. Okay, at the end I will tell you the conclusions. Okay, till that conclusion stay. Okay, stay tuned. Now I can say that means we understood now what is lagging, what is leading. Okay, so what are the conclusions we have taken till now? The first one is length of the phasor should be peak value. Okay, and phasor order of rotation, direction of rotation of the phasor should be anti-clockwise. I will tell you very soon why. Okay, and then means if you sit on voltage, you have to look back for current, so current is lagging behind. If you sit on current, you have to look forward for the voltage because everything is rotating in anti-clockwise direction. So with respect to current, voltage is leading. With respect to voltage, current is lagging. Now, okay, coming to the point. For example, if I have maybe some other sinusoid, basically very soon I will show you sinusoid quantities only can be drawn in a phasor diagram. Why? Because the moment this length is constant, for example, the moment this length is constant, okay, so the moment this length is constant and it is rotating, what is the opposite side? Opposite side is going to be sine of this. Okay, so the moment it's sinusoid, the moment length of the phasor is constant, and if it is rotating with constant velocity, reflection is going to be sinusoid only. So we can say that sinusoid quantities only can be represented in a phasor diagram. For example, if you think otherwise, okay, it will be like this. For example, here speed of the rotation is constant and length of the phasor is constant. That's why we are getting sinusoid in the horizontal reflection. But here speed of the rotation is constant, but length of the phasor here is different. Length of the phasor here is more, length of the phasor here is less, length of the phasor here is more. That's why you are getting other than sinusoid. Here it's altogether different story. Though speed is constant, so length of the phasors are different. So you are going to get other than sinusoid. Okay, so point here is very simple. The moment speed of rotation of phasor is constant, and the moment length of the phasor is constant, automatically reflection will become sinusoid only. So we can say that for sinusoid quantities only we can represent in a phasor diagram. Okay, next coming to the other point. For example, we came to know now that sinusoid quantities only can be represented in a phasor diagram. For example, I have some function f. I have some function f. Now, that function should be sinusoid. So, for example, sinusoid like this, blue line. Okay, sinusoid like this. Then, what will happen? For example, okay, what will happen if you see length of the phasor should be peak value. That peak value is more than voltage, and as of now voltage is starting from 0 and this particular function is starting from 0, both are positive zeros. So my function length of the phasor should be f maximum. Now my function should start from 0 only, horizontal reflection. But if you observe one thing, see here, by the time my black line voltage is completing half the cycle, my blue line new function is completing one cycle. Means that if my black line voltage is rotating with omega, my blue line has to rotate with 2 omega, such that by the time black line complete half cycle, blue line will complete one cycle, one revolution. Basically, means some guys ask me, sir, should we call this as a phasor diagram or vector diagram? Okay, phasor diagram or vector diagram. Actually, the idea we have to see. Okay, because means vector, here diagram is different. Vector in physics is different. Vector in, for example, EM theory, vector in the sense which should have both direction and magnitude. Okay, scalar in the sense without direction. Now, means is our focus is direction? No, our focus is to remember the sinusoid voltage, sinusoid quantities. Okay, to remember sinusoid quantities only we are trying to draw phasors. So it's your wish, you can draw phasor diagram or vector diagram, it's your wish, both are same. Because means from EM theory point of view, voltage is a scalar, current is a vector. Okay, now for example cell. Okay, cell means the same word in different circumstances, automatically the meaning will change. Okay, so cell phone is different, means biologically cell is different. Maybe from police station, cell is different. Okay, so depending upon the application we have to use the word cell, C-E-L-L. In the same way, here there is no concept of, there is no difference between phasor diagram and vector diagram, because our intention is to remember sinusoid quantities only. Okay, now next coming to the point. What is the other conclusion? At the end, I will tell you all the conclusions. Okay, such that you will be able to write. Now, the moment different frequency components are there, because my black is having omega t, my blue is having 2 times omega t. So those two quantities cannot be drawn in a single phasor diagram, because means as of now phase displacement between voltage and this particular function is 0. By the time voltage complete half cycle, this particular function complete full cycle. At that time, what is the phase displacement between voltage and that particular function? 180 degrees. Okay, so the moment this phase displacement between any two quantities is not constant here, it cannot be stationary here. Okay, if it is not stationary, how can we analyze the things? So point here is, means all the quantities represented in a single phasor diagram should be of same frequencies. Different frequency components should not be drawn in one phasor diagram. If you want to draw different frequency components, maybe for 50 Hz draw one phasor diagram, for 100 Hz draw one more phasor diagram, and in that phasor diagram, whatever may be the quantities which are being operated 100 Hz represent there only, and whatever the quantities are operating at 50 Hz represent here. Whatever may be the quantities representing 150 Hz, draw separate phasor diagram, but different frequency components should not be drawn in a single phasor diagram. Okay, now what are the conclusions? Means one more thing is why we have taken anti-clockwise direction. Now if you observe, for example, let me try again. Now, for example, maybe let me think of, okay, see, for example, here, let me draw voltage. Now that voltage is this V maximum, length of the phasor. Now let me think of current here, which is lag behind voltage by pi. This is going to be current, so this is going to be pi. This is going to be pi. Now, if you have to draw that particular current waveform, focus properly. So, after voltage positive 0, current positive 0 is coming after pi angle. So, I have to draw here. This is going to be I max, and this angle is going to be pi. Okay. Now, if I sit on voltage, current is lagging behind because I have to look back because it is anti-clockwise direction. Okay, or if I sit on current, voltage is going to be ahead of you. So with respect to current, voltage is leading, we can say, provided if it is anti-clockwise direction. Now, some people tell if it is clockwise or anti-clockwise, sinusoid only will be the output. No, because for example, this is rotating in this direction. Horizontal reflection, because it will form the circle, horizontal reflection, all will be like this. For example, if it is rotating in opposite direction, in this direction, this is going to be like this reflection. Both are sinusoids only, of course, phase displacement will be there. Okay, so why we have to take anti-clockwise only? Because our ancestors started using anti-clockwise, they standardized the anti-clockwise. Otherwise, we will be confused. For example, if you think of anti-clockwise, if you sit on voltage, you have to look back for current. So current is lagging behind. For example, for the same phasor diagram, if you take clockwise direction, if you assume phasors are rotating in clockwise, if you sit on voltage, current will be ahead of you, current will be leading. Now, in drawing the phasor diagram, now as of now, if I don't give this anti-clockwise or clockwise, how can you say whether current is lagging behind or leading? Okay, means with respect to voltage, current is going to be lagging behind provided if it is anti-clockwise, and with respect to voltage, current is going to be leading if you take clockwise. So, all lagging will become leading will become lagging. So, they standardize because there is no difference. Okay, so they standardize that anti-clockwise direction omega. Okay, so from now onwards, phasor order of rotation, direction of rotation of phasors is in anti-clockwise direction. And let me give a small suggestion here for ESE aspirants. Okay, ESE aspirants, because they have to write in the descriptive paper, if at all, if you have to draw the phasor diagram, means draw the phasor diagram and at least just show a line, show arrow in anti-clockwise direction, they feel happy actually. Okay, now coming to the point, already we know from peak value how to get RMS value. Okay, so for example, how to find RMS value of this particular sinusoid? Peak value divided by root 2. Okay, for example, as a scaling factor, can I say this divided by 2, this divided by 2? Just a scaling factor, because all length of the phasors will be having divided by 2 as a scaling factor. Can I say divided by root 2, divided by root 2? Yes. Okay, so what is divided by root 2? Maximum divided by root 2 is going to be RMS value. So conclusion here is very simple. Okay, means all the phasors, means phasor length either can represent peak value or RMS value. So before starting a problem, you have to know whether the given thing is RMS value or peak value. Okay, so length of the phasor either can represent peak value or RMS value. Okay, for example, voltage given is maybe 100 sine 20t plus 10 degrees. Okay, so means basically in some of the interviews they will ask, okay, at t equal to 1 second, what is the instantaneous value of voltage? Okay, so at t equal to 1 second, v equal to 100 sine 20 plus 30. Can I say sine 30? 0.5 into 100, 50? No. Basically, you have to understand one thing, means this 20t will be in radians and this 10 will be in degrees. So, in order to find out sine of radians plus degrees can be converted into radians or radians can be converted into degrees, such that you have to solve the problem. Okay, anyway, let me come back. If they say v equal to 100 sine 20t plus 10 degrees. Under that conditions, you can write the phasor length as 100 at an angle 10 degrees. Is fine. But while writing this, you have to keep in mind that this 100 is peak value. This 100 is peak value. Now let us think of RMS. Okay, for example, normally if I say how much will be the voltage across maybe wall outlet at our home, roughly we can say 230 volts, single phase. Okay, so what is the 230? Is it RMS value or peak value? RMS. So if they directly say 230 volts means that is it RMS or peak? RMS value. Okay, so logic is very simple. What is that? Unless otherwise specified. Okay, so if they don't specify, if they say some voltage is there, that is 100 at an angle 20 degrees, means that what should be this 100 volts is going to be RMS, because they didn't specify anything. For example, if they give you 100 sine 20t plus 10 degrees, under that conditions 100 at an angle 10 means that it is peak value. So unless otherwise specified, length of the phasor should be RMS value. If they clearly specify, okay, this is length of the phasor which is of peak value like this, then we can consider peak value. Okay, now one more thing we have to understand. Yes, okay, so see here, okay, that red line, this red line is, for example, some voltage, blue line is some other voltage, black line is going to be resultant of both. So if you see here, means blue line is one sinusoid, red is one sinusoid, blue plus red is going to be black, which is again one more sinusoid, just watch this here. Okay, so watch this here. Okay, now let us see about this. Okay, for example, if you think of mathematically, okay, for example, some voltage is there, V1 of some A sine omega t, and some V2 value is there, which is of B sine or maybe cos, okay, omega t plus 45 degrees. Now how much will be V1 plus V2? V1 plus V2 is going to be A sine omega t plus B cos omega t plus 45 degrees. Now what is the net resultant RMS of this? Can I say net resultant RMS is going to be A by root 2 plus B by root 2 square under root? No. Because they are having same frequencies. Okay, so the moment they are having same frequencies, these has to be recombined, and has to be formed into a single sinusoid, and that single sinusoid RMS value is going to be net RMS value. Okay, now for example, if it is A sin omega t plus B cos 3 omega t, under that condition, the net RMS value I can say A by root 2 square plus B by root 2 square under root, we can say. Okay, anyway, our point here is not about RMS value, our point is sinusoid single frequency, so it will be omega t only, So in this, actually in this zip file, they represented that only, red is having some magnitude with some phase displacement, blue is having some magnitude with some other phase displacement, red plus blue is going to be black, is having some other phase displacement. So two sinusoids, because this is going to be very crucial, you will understand very soon in voltage regulations and all. Okay, two sinusoids combinedly will give you of same frequency, will give you only one sinusoid of the same frequency. Okay, now what are the conclusions? If you see? Okay, here in the Phasor concept, point number one, you can make a note of it. Okay, so because we have to understand phasors first, otherwise in transformer some confusions will come, in synchronous you cannot understand. Okay, so our basics should be strong always. If your basics are strong, then later means many books are there and many videos are there, these things will come and help you. So point here is why we are going for phasors. First thing, okay, conclusions of the present discussion. So why we are going for phasors? Point number one, that is in order to avoid drawing the instantaneous waveforms of sinusoid quantities, we are moving from this to new domain called as phasors. Second thing is only sinusoid quantities can be represented in a phasor diagrams. Okay. Third thing is length of the phasor either can represent peak value or RMS value. Fourth thing is means my phasor order of rotation, direction of rotation of the phasor should be in anti-clockwise direction only. Okay. And the fifth thing is means basically if I come back, like length of the phasor is over and RMS value is over. Okay. And I forgot something. What is that? Yeah. Okay. Means all phasors represented in a single phasor diagram should be of same frequency. Okay. All phasors represented in a single phasor diagram should be of same frequency is the final point. Okay. In other words, we can say that different harmonic components, okay, cannot be drawn in a single phasor diagram. Different frequency components or different harmonic components should have different phasor diagrams. Okay. And lag lead concept already we know. Now we will be able to enter into the basics of like AC machines now.